This is the first of several video tutorials going over the math module from the Python standard library. We will go over all the functions in the math module thematically, which means that functions that deal with similar concepts will be discussed in the same tutorial. We'll talk about all the mathematical preliminaries, how to implement the function in Python, etc., etc. In this tutorial, we'll talk about the floor function, the ceil function, the trunc function, and the modf function. Because they are all related to each other, or related to the simple concepts that if you're given a real number, say 9.1, then you can write it as a sum of its integer part 9 and its fractional part 0.1. Similarly, if you have negative 9.1, the integer part is negative 9, the fractional part is negative 0.1. And if you have pi, it's just 3 plus 0.1 for 1 pi, etc., etc. Since this is a tutorial on tutorial series on Python Freelancing, we will try to explore these functions. Using Python as much as possible. So let's go on to our first function, the floor function. To start off our discussion, let's look at the floor function mathematically. So what does the floor function do? It takes in some real number x, which is to say a number that can be written as a decimal, and it outputs the number rounded down. So it's just the largest integer not exceeding x. So for instance, if you take x equals 9.1, the floor of it is just 9. On the other hand, if x is equal to negative 9.1, then the largest integer not exceeding x is negative 10. Perhaps a common mistake is to say negative 9 here, but remember, negative 9 is larger than negative 9.1. So the floor of negative 9.1 is just negative 10. If we want to rephrase everything in terms of the integer part of x, then we see that the floor of x is equal to x itself if x is an integer. It's just n if x is a positive non-integer, and n minus 1 if x is a negative non-integer. Let's look at more examples for practice. So if x is 2, then it's an integer, so it gives back 2. If it's 4.12, then the largest integer not exceeding it is 4, so the floor is just 4. If it's negative 12.12, then negative 13 rather than negative 12 is the largest integer not exceeding it, so the floor is negative 13. The floor of 0 is just 0 because it's an integer. So let's now look at how the floor function is implemented in Python. So as with all of these functions, we're going to have to import the math module first, but that's easy to do. Okay. So the syntax for the math.floor function is just math.floor and then parentheses the number you want to take the floor of. So for instance, the math.floor, the floor of 3.14 is just the math.floor and then parentheses 3.14 and then it gives back 3, which is what we expect from the discussion we just had. If we look at the floor of 1.5, it gives you 1. Floor of 3 gives you 3, etc. And you can keep on generating examples like this. So I highly encourage you to open a Python terminal and look at these examples yourself. Next, let's look at the graph of the floor function. Graphs are really nice to look at when you want to try to understand behaviors of functions, because you'll see how the function grows or how the function is related to other functions with similar graphs. So the tool for this is the matplotlib and the numpy library. So with this piece of code, we can graph out the floor function. We use the numpy floor here for just because it's easier to plot, but you can use it. You can do the same thing using matplotlib. before as well. And you see that the floor function has this staircase-like graph. Strictly speaking, this is not entirely true, because you would recall from, you might remember from pre-calculus that the graph of functions should not have like vertical components like here. So this graph has these vertical lines everywhere above the integer points. So what the graph should really look like is something like this. So you should, instead of these vertical lines, you should have this point on the higher part of the stair ledge and an open point on the base of it. So this would be the actual graph, mathematically speaking. We'll look at this graph again when we look at the ceil function. Let's move on. So let's look. So if you're somewhat familiar with the Python, you'll notice that the math.floor function behaves in a very similar manner as the int function and the integer division by 1 function. So let's try exploring these functions by plugging in various values. So if you plug in 7.12 to all three of these, you'll get back 7, 7, and 7.0 respectively like this. And you can get similar results if you plug in other positive real values. So one obvious difference is that the integer division function gives back a float, but the int and math.floor both give back integers. So just based on this, it seems like the int and math.floor behave in the same way. So let's try look at the negative non-integers. So if we plug in negative 7.12 instead, we in fact get different values for int and math.floor. It gives back negative 7 and negative 8. And negative 7.12, it gives back negative 8.0. So if you turn this into turn this into int, then it would actually coincide with the value for math.floor. So you can see from all of this that int and integer division by 1 behave in a very similar way to math.floor. And int is actually, it gives back the same values if you just restrict the positive integers. We'll come back to the int function when we talk about the trunc function in a few minutes. Let's move on to our next function. The ceil function is very similar to the floor function. So as we said, the floor function is the number rounded down. The ceil function instead is the number rounded up. So if we have x equals to 9.1, then the ceil of that is 10 because it is the smallest integer not going below x. If we have negative 9.1, then the ceil of that is negative 9 because that is the largest, the smallest integer not going below negative 9.1. If we rephrase this in terms of the integer and fractional part, as we did before, then the ceil of x is just x if x is an integer, is the integer part plus 1 if x is a positive non-integer, and it is just the integer part if x is a negative non-integer. Let's look at more examples. So if we take the ceil of 2, then it's just 2, this is an integer. For 4.12, 5 is the smallest integer not going below it, so 5. Negative 12.12, negative 12 is the smallest integer not going below it, so negative 12, and for 0 it's just 0. You can see from all of this, if you compare it to what we said for the floor function, you get this relation that the ceil is just the floor plus 1, provided that x is not an integer. You need this condition because you have examples like this where the ceil of 2 is just equal to 2, and we know that the floor of 2 is just 2. We'll come back to this when we look at the graph of the ceil function in just a second. So let's quickly go over the syntax for the math.ceil function. So as with the floor function, it's quite straightforward. So what you need to do is say math. Of course, you have to import the math library first, as we did for the floor function. But if we do math.ceil, and inside the parentheses, you can just put the number that you want to calculate the ceil of. And then you print it out, and you know that the ceil 1.43 is 2, so we get the correct answer. And we can do something similar to 1.53, negative 6.2, etc. And we all see that the results are what we expect from what we just discussed. Okay, let's now look at the graph of the ceil function. So as we did with the floor function, we can use matplotlib to plot it out. And once again, you have these vertical components around the integer points. Now you'll notice that so as we said before, you're not supposed to have these vertical components if you mathematically speaking, and the graph of the ceil function should look like this instead. Instead of the vertical components, you should have an open point and a closed point, like so. And if we now compare the graph of the ceil function to what we had for the floor function, you'll see that it is very similar. You can see that the ceil function is just the floor function shifted up. So if you shift the whole graph upward, then you get this back. If you just ignore these endpoints. And if you can and maybe you will recall from your pre-calculus class that a relation like this would imply that sort of shifting relation. So if you shift this whole graph up by 1 for the non-integer points, right? So ignoring points like 1, 0, 1, 2, etc., then you get this graph. That's what this relation is showing. Let's now go over the trunc function. So unlike the floor and ceil function, the trunc function is not really the part of the typical mathematical arsenal. At least you'll not learn it in a typical math class. But it's still useful to have in the Python library, so yeah, it's part of the math module. As far as the outputs go, the math.trunc function behaves in the same way as the int function. The only key difference is the really obvious one, where the int function accepts strings as well, strings written as floats. So if you plug in something like a bunch of numbers written as a string, then the int function would accept it. And if you plug in the string, it would output the string given as in integer form. And it would also change the class from string to int. I mean, that's a very obvious difference. I mean, I guess perhaps another subtle point is that the math.trunc function is very obviously a function that's intended for mathematical purposes. So perhaps that would be a reason for choosing that over the int function in certain contexts. So aside from that, yeah, the syntax for the trunc function is pretty straightforward. It's just math.trunc, and then you can put in whatever float you want to put into it. And so if you want to truncate 1.431, it gives back 1. If you want to take a negative number, run truncate that, it gives a negative 1. Likewise, if you have 1.5, yeah, so what the math.trunc function does, it just gives back the integer part. So 1.5 gives you 1, 3 gives you 3, this is an integer, negative 6.2 gives you negative 6, etc., etc. And the outputs are all integer class. And let's also look at the graph of the math.trunc function. And by the way, this and for here we use the math.trunc function in conjunction to the numpy array function. You can use this, by the way, to replace the np.ceil with a math.ceil function over here. I mean, for our purposes, this works just fine, but yeah, this is a construction that you can generalize to our previous examples. So let's look at the graph of the math.trunc function. So it looks like the staircase. Again, the vertical components should not be there, as we said before. You can see that it's an odd function, so it's like symmetric with respect to the origin. And yeah, so it looks like this. The vertical components should not be there, and should be replaced by these endpoints of the integer points. Let's go on to our last function, the modf function. This is also not part of this standard mathematical toolkit, I guess, but in Python it's still there because it can occasionally be useful. And what it does is very simple. It just outputs the fractional part and in the integer part as a list. So let's take a look. If we look at 1.5, well, the fractional part is 0.5 and the integer part is 1.0. Note that the integer part is returned as a float instead of an int. Likewise, if you plug in an integer, it gives you back 0 and 3.0. Occasionally you get something weird like this where you get this weird fractional part. The 0. It's basically correct, except you have this like small 1/8 thing. I think this has to do with how the modf function is implemented in Python, but that's beyond the scope of this tutorial. And likewise, we can look at all these other examples. Once again, I'll encourage you to explore these examples yourself. And if you're careful, you'll notice that the first component, the second component of the modf function is the same as the trunc function. So if we try to let's try 1.4 here, and if we attach the second component, we get something like this. If we try using the trunc function, we can do this. Okay, so they give you the same output except that the modf function gives you a float and the trunc function gives you an int. If you try doing a negative guy, again you get the same number except that the modf gives you a float and trunc gives you an int. Let's now look at the graph of the modf function. As we just said, the second component is just the same as the trunc component, provided again that you convert between int and floats. So if we just look at the first component of modf, which is just the fractional part of the number, you get this thing, this zigzaggy thing, and as we said with the previous three graphs, these vertical components should not be there, and instead there should be filled in. There should be a open points here, and then there should be closed off points here, and open here, closed here, etc. And as I said, the second component of the modf function gives you the same graph as the trunc function, like so. So I guess that's it for today. We went over all four functions, the floor function, ceil function, trunc function, and the modf function. And to cap it off, again, they're all related to the fact that you can write a real number x in terms of its integer part and its fractional part. And these functions are just ways of manipulating these in the Python library. Okay, so that's the end of the first tutorial, and I look forward to I'll see you guys in the next one.